Hi students. So today we are starting lecture 37 and this is going to be a short lecture and I'm going to discuss about the time to climb for an airplane. So this essentially builds up on the concept of rate of climb which we discussed in our previous lecture and it tries to calculate the time to climb. I'm Dr. Ranjan Ganguly. Now let's again look at this picture we have considered before. So this is the airplane in the climb mode and you have the horizontal, you have the flight path, and you have the angle theta between the horizontal and the flight path. So essentially when the aircraft is climbing, this is the path it takes. And we have discussed in our lecture before the different forces which act on the aircraft, specifically the thrust, the drag, the lift, and the weight. Now look at the geometry of the aircraft in terms of the velocity. So essentially the velocity is in the same direction as the flight path which is given here, and the angle between the horizontal and this velocity is given by theta. So we saw that the rate of climb was v infinity sine theta. Now if you start thinking in terms of altitude or height from the ground or height in general, you are going to figure out that rate of climb is dh by dt. So essentially it is the rate of change of altitude with time. So that is the definition of rate of climb in terms of calculus, and what it's going to do is it's going to get some idea about the time it requires to climb from a given altitude to a different altitude. So let's try to get the equation for that. So we are going to look at the equation for time to climb from height h1 to h2. So essentially now consider you are at height h1 and you have to go to h2. So of course in an airplane you have to go like this. So you have a certain velocity. You have to go in this direction. And so let's start with the equation for rate of climb, that is dh by dt. I can rewrite it as dt is dh by r by c, which is the rate of climb, and I can integrate this equation to get t equals h1 to h2 dh by r by c. So this integral is essentially the time to climb from height h1 to h2 or altitude h1 to h2. So now many a time we are looking for the time to climb from sea level. So here I have shown the sea level situation, and let's say there is an aircraft and it's taking off from sea level and then it's climbing to some altitude h2. So here I can say t is integral 0 to h2 dh by r by c. So again this integral can be found provided we know the variation of r by c with respect to h. So in general, the rate of climb, of course, would vary with h. So we would get some kind of graph like this if we were to calculate the rate of climb at different h values. And then we can calculate this integral. T is integral 0 to h2. So h is 0 here, h2 here. These are the bounds of the definite integral. You have dh here. Dh is essentially a small increment in h. So from calculus we know that this is a very small change in this length h, and so t would be simply this integral. And once we know the variation of 1 by r by c, which I have shown here, some kind of variation like this, all we need to do is calculate the area under this red curve. Now of course if you have studied numerical analysis or computation, you would know that there are many numerical methods to find this kind of integral. You can use the trapezoidal rule, which essentially sums this integral in terms of rectangles. You can use the Simpson rule, or you can also use some of the Gauss quadrature formula. So essentially it's very easy to call a simple function and to calculate this definite integral here. So to summarize this lecture, we have now extended the concept of rate of climb to time to climb. And this is an important performance metric because in case of many aircraft, it's important to know how much time it's going to take to climb from sea level to a given height, because that's a performance metric which you need in many cases because you don't want to hang around too long in the low altitude regions because there are a lot of planes which fly there, and also certain height, certain altitude are reserved for certain type of aircraft. So you want the aircraft to use this rate of climb r by c to get into the region of airspace where it is essentially permitted to fly. This is important not only for the typical passenger jets which we see around, but also for various smaller airplanes which fly for pilot training schools and so on. And of course, this integral can be easily found using numerical integration, or if you have some kind of closed form relationship for r by c, then you can also use classical integration methods here. So this essentially ends our thinking about the performance aspect. So we have studied a lot about level cruise flight. You have now become familiar with the concepts of available power and required power, and also rate of climb and time to climb. And next video I'm going to talk about endurance and range of aircraft.